So hello and welcome everyone to the CDY-Initiative series of seminars. Today is actually the last day in the CDY Extreme Non-Thermal Universe series focusing on extragalactic physics for the summer. We are going to take a pause for the summer and then come back in the fall. So please stay tuned. Today's talk is entitled Radiation Mechanisms of FRBs, Fast Radio Bursts, and will be given by Professor Yuri Labarski. Yuri is currently at Ben-Gurion University. He graduated from Kharkiv University, got a PhD in Space Research Institute in Moscow, worked at the institute, and subsequently moved to the Institute of Radio Astronomy at Kharkiv. Since 2000, he has been at the Ben-Gurion University, where he's currently professor in the Department of Physics. Yuri's expertise covers several areas in high energy astrophysics. He has worked on pulsar emission mechanisms, physics of pulsar wind nebulae, clarions, magnetic field reconnection, relativistic jets, relativistic plasma, fast radio bursts. So it's with pleasure that we welcome Yuri Labarski and get started. Yuri, please share your screen. If you prefer, people can ask questions during your talk. Otherwise, what we've been doing normally is at the end of the talk, there's a discussion, questions on the talk itself. And then we generally have a discussion on any topic of high energy astrophysics that is relevant.
Okay.
Please go ahead. And if you're not speaking, I would just ask you to please mute. Thank you.
Thank you, Reshmi, for introduction. Oh, now I think everybody see my screen, yes?
Yes, we do see your screen.
Okay, hello everybody. I am going to overview attempts to understand physics of fast radio bursts, which is one of the hottest topics in the modern astrophysics. Here we have coherent emission, and therefore a great deal of plasma physics is involved, and therefore I try to explain this physics at the very basic level. First of all, what do we see? Okay. Fast radio bursts are pulses of radio emission of millisecond duration coming from different directions, roughly isotropically, from typically cosmological distances. The luminosity, in fact, isotropic luminosity is very high. It corresponds to the total emitted energy, isotropic emitted energy presented here. Please note very large scatter in the energy, but all this energy are extremely high, especially taking into account that all this energy is emitted for 1 millisecond in the radio band. Most of FRBs are one-off events. So we see one burst and that's it. There is a small fraction of repeaters, which exhibit few, maybe many bursts distributed more or less chaotically in time. The spectrum could be hardly described by something like single power law. Presumably it is more or less narrow band with a very complicated frequency structure. The radiation is strongly polarized, typically linearly. Sometimes the degree of polarization reaches 100%. Sometimes elliptical polarization is also observed. These bursts are observed only in the radio band. Nothing was seen in other bands. The only exception, during one of the X-ray flares from a galactic magnetar, a very weak FRB was detected, much weaker than these FRBs. This in fact means that the scattering energy is even larger than presented here, so we presumably have much more weaker FRBs, which we simply do not see from other galaxies. This is shortly what do we see. The most important point is that this huge luminosity implies coherent emission mechanism. Therefore, here, in fact, macroscopic numbers of particles move coherently radiating together. Of course, this means that the radiation mechanism is, in fact, the collective plasma radiation process. In plasma, due to long-range direction, coherent motions of large ensembles of particles could be excited relatively easily. But the important point is that the plasma affects also the radiation process and the propagation of the waves. All this should be considered self-consistently, and any reasonable model must answer the following basic questions. First of all, what electromagnetic waves could propagate in plasma at the assumed conditions? Then, how could these waves be excited? An important question, how could these waves escape as a radio wave? If could, maybe not. And at last, only, what are the properties of the outgoing radiation? I'm going to present two radiation mechanisms of very different classes, and to describe shortly how they could work in the environment of magnetar flares, because magnetars are considered as the most plausible progenitors of FRBs. At the end, if I have time, I discuss a few propagation effects which are of crucial importance. So the first class of mechanisms widely discussed, maser. The basic picture is well known, based on the notion of induced emission. Therefore, the quantum picture is assumed. Any photon with energy equal to the difference energy between two energy levels could not only be absorbed by triggering the upward transition of electrons, of an electron, but also it could trigger downward transition with the emission of additional photon. In this case, if the upper level is overpopulated, the net result of this transition is a radiation, and therefore a seed photon produces an avalanche of photon, therefore powerful beam. This is correct, but we have to take into account that, in fact, we deal with classical systems, which could be completely described in the scope of classical electrodynamics and physics. Classically, we deal with an unstable plasma, resonantly unstable, such that incident wave satisfying the resonant condition triggers in this plasma modulation of currents and charges, which radiate in phase with this wave, and therefore this wave is amplified. So these two pictures are correct. Quantum pictures, paradoxically, more vivid and has a significant heuristic power, because it's relatively easily just looking at the system to predict that it is unstable because it is inversely populated. But again, everything could be described by classical physics. When we are talking about FRBs, people discuss synchrotron maze. Again, the basic picture is simple. Particles rotate in magnetic field. One could easily imagine a ring-like distribution in the phase space. Spatial distribution may be homogeneous. So there are no electrons with energy smaller than something. Therefore, this is inverse population, and therefore one could predict induced emission and therefore maser. Classically, this means that this system is unstable with respect to modulation of the ring and formation of bunches rotating and radiating coherently. The picture is simple, but there are few subtle points. It shows that the situation is not very simple. First of all, there is no maser in a system of equidistant energy levels. Just because even if the level number n is overpopulated, electrons could emit jumping downwards, but they could also absorb the same frequency jumping upwards. And absorption wins. Therefore, maser is possible in the system, for example, of linear oscillators. Therefore, the system of relativistic Landau levels is equidistant, the cyclotron maser could work only due to small Lyubarsky corrections, and therefore cyclotron maser is weak. If we are talking about synchrotron maser, about relativistic particles, there is no such a problem because relativistic Landau levels are not equidistant. But there is another problem. By synchrotron, we typically mean the radiation at very high harmonics of the rotational frequency, such that harmonics overlap and the spectrum is continuous. In this case, each frequency could be emitted and absorbed by electrons with different energy. In this case, even if inverse population is formed, so again, let's assume that we have a ring-like distribution. Here we have inverse population, therefore induced emission dominates, but radiation from these electrons could be absorbed by electrons with higher energy. It was found already in the 60s. Because of this effect, synchrotron maser could work only if the energy distribution is unrealistically narrow, in fact, delta function. So situation is not very simple, and more careful consideration is necessary. First of all this overlapping does not work for the few first harmonics. In this case, these harmonics do not overlap unless the energy distribution is not very wide. Scattering energy is smaller than energy, that's okay, no overlapping. Therefore, maser could work. But in this case, the frequency is very small. Therefore, the question is whether the wave with the frequency that's small could propagate. The condition is that frequency exceeds plasma frequency. Plasma, again, we deal with the relativistic systems, so both Larmor frequency and plasma frequency I take for relativistic particles, take into account a large mass. Therefore, condition that this frequency exceeds the plasma frequency may be written as condition for the well-known magnetization parameter, which is the ratio of the magnetic to the plasma energy density, which could be presented as the ratio of these two frequencies squared. So this maser at few first harmonics could work only if sigma larger than unity. So only if magnetization is extremely high. If magnetization is smaller than unity, radiation is possible only at higher harmonics. In fact, at frequency higher than the plasma frequency. In this case, one has to take into account that if the frequency is not much higher than the plasma frequency, the propagation is affected by the plasma, and the velocity of the waves becomes superluminous. In this case, the synchrotron emission is strongly suppressed. This is called the rising effect. And the higher the energy of electron, the stronger the suppression is. The emission is suppressed, and therefore absorption is suppressed. In this case, maser could work because both emission and absorption are suppressed, but absorption is suppressed stronger. Therefore, the net result is the maser emission. In the 60s, it was predicted already in the 60s, but people thought of normal plasma with some admixture of electrostatic electrons, with the normal plasma providing the dispersion. If the density of the relativistic electrons is high enough, we need normal plasma. And in this case, maser could work at the frequency, which is a bit larger than the plasma frequency. Sigma is smaller than unity, but to the power 1/4. And at some higher harmonics of Larmor frequency. But in all practical cases, these harmonics are not too high, as, for example, gamma cube harmonics for standard synchrotron. So the bottom line is that synchrotron maser could work at not too high harmonics, and therefore, in order to get the radio emission, we need very high magnetic field. Okay, this is the first. The second, the question is how to produce ring-like distribution, which is very non-trivial. It was assumed long ago that an appropriate site is the front of relativistic magnetized shock. At the shock front, plasma stops and particles begin to rotate in the enhanced magnetic field. So ring-like distribution is formed naturally. This idea was supported by simulations of many groups. There are some couple of results of such simulations for different magnetization. This is density. This is upstream, flow from the right to the left, and density jump. And you see that magnetic and electric field exhibit strong fluctuations. This is electromagnetic radiation at the frequency a bit larger than the plasma frequency downstream of the shock. even one could see a ring-like distribution in the phase space at the shock front. The mechanism is quite efficient. Up to a few percent of the upstream energy could be converted into this radiation. Efficiency depends on magnetization. It is maximal at moderate magnetization and decreases towards higher magnetization at smaller magnetization. So relativistic strongly magnetized shock could in principle be sources of strong coherent radio emission. Such shocks could be met at different environments. I try to explain how it would work in magnetron flares a bit later, but for a while I would like to present the second radiation mechanism, which belongs to the class of the so-called antenna mechanisms. What is antenna? It's just linear current with variable current, a linear conductor with variable current. Such linear currents could be naturally formed during the reconnection process. As Lorenzo Cironi explained us 2 weeks ago, the reconnection process in the current sheet separating oppositely directed magnetic field proceeds via formation of the so-called magnetic islands, which are in fact linear currents. Islands appear in cross-section. These currents are variable, therefore one could say that they emit radiation. This analogy is not very useful because we deal with MHD system. All characteristic time scales are larger than the plasma time scales, and therefore only MHD waves could be excited. Therefore, this is not a standard emission of antenna into vacuum. At the language of MHD, the situation could be described as follows. These magnetic islands continuously collide and merge, as Lorenzo explained it us. The reason is very simple: parallel currents attract each other. Here in simulations, you see color here is horizontal velocity. You see pairs of islands moving one toward another. When two islands collide, they excite perturbation of the surrounding magnetic field, and any perturbation propagates away in the form of MHD waves. And therefore, such system emits MHD waves. And the question is how these waves could be, if could, converted to radio emission. There are 2 types of MHD waves. Alvean waves, which remind waves in the stretched string. In this case, strings are magnetic field lines. These waves propagate along the string, therefore along the magnetic field line. And therefore they are of no interest for us because they remain close to the current sheet. If they are excited here, they remain here. We are interested in another type of MHD waves, magnetosonic waves. These are, in fact, sonic waves, which with the compression or rarefaction of the plasma density. But in this case, because magnetic field is frozen into the plasma, magnetic field also oscillates. And the restoring force in these sonic waves is provided by the magnetic pressure, not by the plasma pressure. This is magnetosonic wave, which pretty well propagates across the magnetic field lines. Simulations show that reconnected current sheets do produce such magnetosonic noise. Here are simulations. Current sheet here is vertical. Reconnection, reconnection happens here. Color here is the Poynting flux. Blue to the left, red to the right. And you see spherical, no, cylindrical, in fact, pulses produced by the merging of magnetic islands and propagating away. According to simulations, the power of this magnetosonic noise is about 0.5% of the energy dissipated in the current sheet. The width of these pulses is comparable with the size of the islands, which scales with the Larmor radius of particles in the current sheet. So if the Larmor radius is in the radio band, we could produce radio emission, again, if these waves are converted into radio waves. This is indeed possible if we consider a connection in highly magnetized system, namely in the system with sigma much larger than unity. To see this, let us consider properties of magnetosonic waves in such a plasma. This wave is longitudinal. Plasma oscillates in the direction of the motion, in the direction of the wave. However, magnetic field is perpendicular. Electric field here is excited by plasma motion. It is V cross B. Therefore, it is directed perpendicularly to the plane of this screen. Therefore, this is transverse electromagnetic wave. It is longitudinal hydrodynamic wave, but it is transverse electromagnetic wave. Velocity of the sound wave is just square root of pressure over energy. Pressure is magnetic pressure. Energy here is total pressure of plasma and magnetic field. And therefore, if sigma is large, so magnetic energy significantly exceeds the plasma energy, the velocity of the wave goes to the speed of light. The ratio of the electric and magnetic field in this wave is determined by the Faraday law. This ratio is equal to the ratio of the velocity of the wave to the speed of light. And it goes again to the unity when sigma goes to the infinity. And conductivity current, which could be found from the Ampere law, goes to zero. Therefore, if these waves propagate towards smaller and smaller plasma density, they smoothly become electromagnetic transverse waves, polarized, 100% polarized perpendicularly to the background magnetic field. So this, of course, they could be absorbed by many other processes, which I maybe discuss later if I have time. But in principle, one could produce radio emission via magnetic reconnection in the relativistic current sheet. Again, highly magnetized reconnecting system could be found in different environment. I try to explain how it could work in magnetized flares now. Because for a while I presented two mechanisms. Now let us discuss shortly magnetar flares. Magnetars are considered as the most probable progenitors of FRBs by many reasons. First of all, the energy budget is sufficient. All activity of magnetars is fed by the energy stored in the magnetic field of the magnetar in the magnetosphere, and total energy is large enough. Magnetars exhibit flares with very different energy, and energy of strong flares is again more than sufficient in order to produce FRBs. One more important point is that the rate of magnetar flares is comfortably above the rate of FRBs. So they could be progenitor, because the rate of FRBs is very high. It's much larger than the rate of GRBs, for example. So we need frequent events. An important point is the duration of the flare is typically significantly larger than the millisecond. But the reason is that the energy released in the flare need time to be radiated away. This is, in fact, the duration of the flare is determined by the cooling rate of the fireball produced in the magnetosphere of the magnetar during the energy release. The energy release presumably proceeds at the millisecond time scale. First of all, this is characteristic time scale in the inner magnetosphere, which is determined by Alfvén crossing time with the inner magnetosphere. And moreover, this is supported by observations. Here are light curve of giant flare. This is a typical light curve. We see strong, the so-called hard peak, which was not resolved because the flux in the peak was so high that all detectors were saturated. The duration of this peak was a fraction of half a second or so, and it was followed by the quasi-thermal tail. This tail was emitted by a fireball slowly radiating away the released energy. This hard spike was resolved recently in the giant flare from an extragalactic magnet. In this case, only hard spike was observed. This tail was too big. And you now see that there is a very strong peak at the millisecond time scale, after which we have gradual decreasing of the flux. This supports the conjecture that the energy releases in the magnetosphere very rapidly, abruptly at the millisecond time scale. In this case, how this abrupt energy release could produce the FRB? Independently of any energy release mechanism, the magnetosphere is shaken by this energy release because the magnetic field is restructured somehow, or MHD waves are excited, does not matter. This shaken magnetosphere produces magnetic perturbation which propagates away in the form of MHD, strong MHD pulse, independently of any details of how the energy released and what happens exactly with the magnetosphere. The FRB could be related to this strong millisecond duration MHD pulse. The amplitude of this pulse decreases as 1 over r. This is in fact electromagnetic pulse. It propagates with the relativistic velocity, practically with the speed of light. The background field in the magnetosphere decreases much faster. Therefore, the ratio of the amplitude of the pulse and the background field becomes very large. At the light cylinder, where the magnetosphere goes into the magnetar wind, magnetar produces wind just like pulsar. It's rotating magnetosphere, it produces relativistic highly magnetized wind. At the light cylinder, the ratio of the amplitude of the pulse to the magnetic field in the wind or the background magnetic field is very high. Therefore, we have such a picture, very strong pulse in a very weak background. The total energy of the pulse is determined by the magnetic field and by the duration. Duration presumably is about a millisecond. This is the wave. It propagates with the speed of light. Therefore, in this wave, electric field is equal to the magnetic field. Plasma in this wave is dragged by the pulse, but eventually it lags behind. The velocity here, velocity of plasma, may be found just as the velocity of the zero electric field frame. This is E over B. Total electric field over total B. Electric field is equal to the magnetic field in the pulse, but magnetic field is the field in the pulse plus the background field, which is small. Therefore, velocity of the plasma is very close to the speed of light, but of course smaller than the speed of this waveform. Therefore, plasma and magnetic flux, they are dragged by this pulse outside the magnetosphere. But gradually, this is substituted by plasma and magnetic field from the wind, whereas magnetic flux and plasma dragged initially lag behind the pulse. And the pulse propagates relativistically. So we have large energy ejected with relativistic velocity in highly magnetized system. The question is how to produce radio emission. We have two radiation mechanisms. The first one is synchrotron shock. So we need strong shock. How to produce shock in this case? The pulse must collide with something heavy and slow. There are a few possibilities. The first, the most natural, is that the pulse propagates in the wind far away and eventually enters the nebula, inflated in the interstellar medium by the magnetar wind, just like pulsar wind nebula. Such nebulae are observed around magnetars. In this case, strong shock is produced and it could radiate. The problem is that this happens pretty far from the magnetar at large distance, because the termination shock of the magnetar wind is pretty far. And therefore, because the emitted frequency is proportional to the Larmor frequency, it is determined by the magnetic field in the pulse. Magnetic field decreases as 1 over r. At this distance, it remains high enough to produce radio emission, only if the total energy of the magnetic pulse is extremely large, comparable with the total energy stored in the magnetosphere of the magnetar. Of course, this is incompatible with the existence of repeaters. Their energy budget definitely much smaller. But even ubiquity of one-offs evidences for a relatively moderate energy budget of most of FRBs. Maybe in some extreme cases this model works, but not in every case. We need a shock closer to the magnet. Another idea was that the pulse collides with the baryonic cloud ejected during the previous giant flare. Giant flares do eject mildly relativistic baryonic clouds. This is the observational fact. But for this model to work, we need at least 2 giant flares during one day, which is a very strong assumption. Another problem with this model is that this cloud is hardly ever strongly magnetized, but we need magnetized shock. And what is more important, because this is baryonic plasma, even magnetized shock in this plasma must emit at the proton Larmor frequency, not at the electron Larmor frequency. This frequency is too low. What is remaining is to assume that the shock arises in the magnetar wind itself. But for this to happen, the wind must be very heavily loaded by plasma, very slow and very powerful. One could get reasonable parameters of FRB emission only if magnetization of the wind is smaller than 100. Lorentz factor is about 10, and the total power of the wind significantly exceeds the standard spin down power, even for magnetar with 1 second period. Note that magnetar slows down for 1 second for about 30 years. Therefore, there is no much sense to consider magnetars with smaller periods. It is not clear how such a heavy, powerful wind could be produced, but it's not impossible. And if we assume that this is the case, one could get reasonable parameters, radiation in the radio band. Efficiency of this emission in all these models is some fraction of the total energy of the pulse. The fraction is just determined by the efficiency of the shock, of the emission of the shock. Important point that in this model, the emitted frequency, which is determined by the Larmor frequency, is only weakly dependent on the pulse energy, which is good because the scattering energies, the observed scattering energies of FRBs is very high. The reason is that the magnetic field is inversely proportional to the distance, in this case to the shock position, and to the square root of the energy, because energy is magnetic energy. The larger than the energy of the pulse, the further out shock propagates. Therefore, these two quantities nearly cancel each other. Therefore, pulses with very different energy could produce radiation with different power, but within more or less the same frequency band, which is good. But still, large caveat is the assumption on a very unusual pulsar wind. Magnetar wind. Now, how could work the second mechanism, the reconnection? Of course, during the magnetar flare, reconnection happens even within the magnetosphere itself, deep inside the magnetosphere. However, deep inside the magnetosphere, all characteristic plasma parameters, plasma frequency, Larmor frequency, are too high. Therefore, it is not so clear how to produce emission in the gigahertz band. What is more important, as I hope to show later, even if by some mechanism the gigahertz emission with the typical FRB power were produced deep inside the magnetosphere, this radiation could not escape. I try to explain this later. So, but for a while, the point is that we need a source somewhere in the outer magnetosphere or beyond the magnetosphere within the magnetar wind. In this case, the natural site for the reconnection is the current sheet separating just beyond the magnetosphere the oppositely directed magnetic field in the pulsar wind. This is just the striped pulsar wind, the same configuration. Rotating magnetar magnetosphere produces in the equatorial band alternating magnetic field, and this magnetic fields of opposite sign are separated by oscillating current sheet. When the strong magnetic pulse produced by the flare enter the current sheet zone, it sharply squeezes the current sheet and pushes it away. And thus, violet reconnection is triggered. So this could produce radio emission via the mechanism I described. Here one could produce reasonable parameters for the typical energies of FRB, but not for weak FRBs. The problem is the same. The frequency is proportional to the Larmor frequency. In this case, the site of the emission is fixed. This is Larmor, this is light cylinder. Therefore, the frequency is roughly proportional to the square root of the pulse energy, and therefore roughly to the square root of the FRB energy. Therefore, the dependence of the emitted frequency on the energy of the FRB is very high. This model could not explain all wide variety of FRB luminosities. In order to produce weaker FRBs, we need reconnection inside the light cylinder, but somewhere in the outer magnetosphere, but inside the light cylinder where magnetic field is large. Maybe there is just an idea that this could happen because during magnetar flare triggered by the star quake, an Alven wave, large-scale strong Alven wave is generated in the magnetosphere, and in the outer magnetosphere, this Alven wave produces what is called plasmoid, which is detached from the magnetospheric field and which is ejected away. Because this plasmoid is detached from the magnetospheric wind, this assumes reconnection. And therefore, probably in the course of this reconnection, radio emission could be produced. But this is still a very vague idea. Nobody tried to develop a quantitative model. So, for a while, I presented two mechanisms and show how they, in principle, could work during the magnetar flare. But as I said, and how they could produce the radio emission. But as I said, in all these cases, propagation effects are extremely important in order to find the parameters of the outgoing emission, and therefore I In the remaining time, I try to touch upon a little bit few propagation effects, not all of them, too many. The first important issue is polarization. In principle, polarization is formed far away from the source. The reason is that the radiation propagates in the form of two orthogonally polarized normal modes. For example, let us consider electron-positron plasma. In this case, normal modes are linearly polarized. One mode is polarized perpendicularly to the magnetic field. The second in the plane set by the magnetic field in the direction of the wave. When the mode propagates, magnetic field varies along the ray, and the polarization is adjusted to the local direction of the magnetic field if this condition is fulfilled. Here, L is in homogeneity scale, and N are, and 1 and 2 are refraction indexes of two waves. Therefore, this assumes that the spatial beating scale between two modes is much smaller than the inhomogeneity scale. Taking into account that the ratio of the inhomogeneity scale to the wavelength is extremely large in astrophysical systems, this condition is typically fulfilled far away from the source. Only when the plasma density drops significantly, this condition is violated. Therefore, to pretty far distances, radiation propagates in the form of two independent normal modes, and it is adjusted to the local direction of the magnetic field. The polarization of the outgoing radiation is formed in the so-called polarization limiting region, where this parameter is of the order of unity. The parameters of the outgoing polarization is determined by the direction of magnetic field here, not at the source. Moreover, if the magnetic field turns even within this region, because here adiabatic adjustment is already impossible, linearly polarized emission could become generally elliptically polarized. What all this means for our models? The situation in the synchrotron shock model is very simple. In this case, shock radiates directly into the magnetar wind. In the wind is azimuthal and remains azimuthal till the very large distances, and therefore the direction of the magnetic field does not change, and therefore polarization remains initial polarization, because initially it was polarized perpendicularly to the magnetic field. Therefore, along the rotational axis of magnetar, it remains polarized in this direction. So in this model, polarization is always fixed. This is indeed observed in some repeaters. In some repeaters, position angle remains the same in all bursts. But there are other bursts where polarization angle varies from burst to burst. And moreover, circular polarization are also observed in some cases, because synchrotron shock produces linear polarization. The reconnection model is richer if we consider polarization. Initially, only 100% polarized radiation waves are produced, polarized perpendicularly to the local magnetic field. This happens within the strong pulse. And the magnetic field in the pulse initially is the magnetospheric magnetic field dragged by the pulse. Only gradually this magnetic flux is substituted by the magnetic flux from the wind, where magnetic field is azimuthal. Here, magnetic field is quite arbitrary. It's determined by the direction of the magnetic field at the side of the flame. There should be a transition region between these two regions with magnetic field differently directed. The width of this region must be determined by the reconnection, presumably. And the polarization of the outgoing emission is determined by the properties of this region. If the condition of adiabatic adjustment is fulfilled in this narrow region, then polarization remains 100% linearly polarized, and the position angle is gradually adjusted and become perpendicular to the azimuthal magnetic field in the wind, and therefore directed along the rotational axis of the magnet. If this condition is violated in this region, a variety of polarization patterns is possible. One could get polarization, practically arbitrary polarization angle, and moreover, one could get even some fraction of elliptically polarized radiation. Of course, this demands more careful study of what happens here, but it is clear that this model is richer from the point of view of polarization. The next question is escape of waves. There is a long list of processes which could affect escape of the waves. I'm not going to discuss all of them, just as an example. Let us discuss why FRB could not escape from deep inside the pulsar magnetosphere. Excuse me, magnetar magnetosphere. Deep inside the magnetar magnetosphere, Larmor frequency is very high. This is definitely the case. Plasma density is typically also high, so that the plasma frequency significantly exceeds the radio frequency. Again, in this case, only MHD waves could propagate, and if we are interested in potential radio emission, we are interested in fast magnetosonic waves. Let's assume that there is a source of fast magnetosonic waves with gigahertz frequency band and with the power of typical for FRB. Power is very large, therefore one has to take into account nonlinear interaction of waves. And the strongest process is three-wave interaction, the decay of a wave into two waves, or opposite, merging of two waves into single one. This is possible if these conservation laws are fulfilled. Specifically for MHD waves, they are fulfilled for two processes: decay of magnetosonic wave into magnetosonic and Albion waves, and reverse, or decay of magnetosonic into two Albion waves. This magnetosonic wave could in turn decay into Albion, so eventually this process produces only Albion waves, which could not escape by many reasons I have no time to discuss. The rate of this process, as of any three-wave process, may be presented very simply. It is proportional to the frequency of the wave and to the ratio of the wave energy to the energy of the background field. Close to the magnetar surface, magnetar field is extremely large, therefore this rate is small. However, when the wave propagates outwards, this ratio increases rapidly because the background magnetic field rapidly decreases. And already at the distance of 10 stellar radii, the rate of this transformation becomes larger than the propagation rate. Therefore, magnetosonic waves all convert into Albion waves, and then they, due to Albion cascade, eventually decay. Therefore, again, even if by some mechanism FRBs in the gigahertz band with typical FRB power were generated within the pulsar magnetosphere, they could not escape. Of course, this process works everywhere outside in the outer magnetosphere, in the pulsar, in the magnetar wind, but in the outer magnetosphere, in the magnetar wind, already strong pulse is formed, which propagates relativistically. In this case, this process is suppressed by relativistic slowing down of time. And therefore, magnetosonic waves generated in the reconnection process could survive. And last, I have a couple of minutes, I would like to discuss one more nonlinear process, which could not prevent escape of the wave, but could significantly affect the observed properties. I mean modulation and filamentation instabilities. These processes are very well known in the nonlinear optics. For example, if a beam propagates in the medium with the refraction index, which increases with the radiation intensity, the rays are focused towards the axis of the beam. This is called self-focusing. In astrophysics, we have very wide beams. They could not be focused as a whole. In this case, self-focusing leads to filamentation. Wide beam splits into many sub-beams. The width of these sub-beams is determined by the properties of the plasma. So this process does not prevent the waves from escape, but there are a couple of interesting observational consequences. First of all, when this radiation escaped from the plasma cloud, these narrow beams expand due to refraction, and therefore short pulses could be widened because of this expansion. Characteristic scattering angle depends on parameters of the plasma. For example, if we consider magnetar wind, which consists of electron-positron plasma, and assume that this wind is cold. In this case, scattering time scale is of the order of micro or millisecond. A millisecond is comparable with the observed width of the pulse, and therefore this consideration could place limits on the parameter of the magnetar wind, on the density and the Lorentz factor of the wind. If the wind is warm, this scattering time scale is very short. But there is another effect, because these beams overlap. Due to interference between these beams, frequency modulation appears at the frequency band, which is about 1 over scattering time. For the warm wind, this modulation frequency band is about 100 megahertz, and it is very close to what is observed in a few FRBs. This is for if the radiation propagates in electron-positron plasma. In principle, baryon plasma could also present close to the magnet. If it is not too far, again, filamentation instability work, but at different parameters. And this instability also results in frequency modulation in the sub-gigahertz band. Moreover, in the baryonic plasma, there is another process, the so-called modulation instability. Modulation instability means that each sub-beam becomes modulated. So it splits into many balance, into many peaks. Modulation instability is impossible in pair plasma, but it does work in baryon plasma. The time scale of these peaks is about 10 microseconds. They could produce fine time structure of FRBs, which sometimes observed in some FRBs. All this is only preliminary estimates. Of course, more detailed study, first of all, numerical study is necessary. But I tried to show that there is a variety of plasma processes which could work in FRBs and which could determine the properties of FRBs. So the conclusion is that coherent emission from FRBs is plasma collective emission process. And I presented two radiation mechanisms, each of which could work at magnetar, at least during magnetar flares. Maybe they could also work at different environment. This has not been studied yet. And what I would like to stress again, that propagation effects are of crucial importance when we deal with compact radio sources at all and with powerful radio sources, especially because in this case, nonlinear processes come into play. Thank you. That's it. What I was going to tell.
Thank you, Yuri. Thanks for a great talk. So we have time for questions. So let's see. Let's start with Kota. Kota, please go ahead.
Yuri, thank you very much for the great talk. And I have questions about the induced competence. So I think that, do you think that this is a, I think that you would probably require the high magnetization or some condition to avoid the induced competence scattering. So do you think that this is always satisfied, or in the probably my guess that in some cases it might not be satisfied, right? The induced competence can also.
Specifically, if we discuss these two mechanisms, in the case of connection, there is no Thomson scattering because this system is strongly magnetized. In the case of the synchrotron shock, the radiation goes into the magnetar wind, and in this case, in principle, induced scattering could work. But first of all, people made estimates and showed that it could, even if it works marginally. But what is important in the case if the filamentation instability works and the magnetar wind is cold, this what happens? The plasma density is modulated. If the ponderomotive force of the wave is larger than the plasma pressure, plasma is evacuated from these beams. All plasma is gathered into walls between the beams. In this case, induced scattering is suppressed because there is no plasma. Most of the radiation propagates in vacuum.
Okay, a bit pushed. I see. So also, can I ask one more secondary question? That you didn't discuss the possibility of the FRB emission, from the inside the magnetosphere. So that because people discuss these possibilities too, and but do you think that these possibilities have difficulties? So that is why you didn't mention there a lot, because you focus on the.
Sorry, I didn't understand the question. Because
So I think that people discuss some coherent curvature or some, some coherent emission producing the magnetospheres, and then, but you didn't discuss these. But do you find these actually mechanisms have some difficulties? That is the reason.
First of all, I don't think that these models are physical because they are based on manipulation with the conditions well beyond their range of applicability. But in any case, what I try to demonstrate that independently of the radiation mechanism, nothing could escape from deep inside the magnetosphere.
I see. So do you think that this actually escape problems are very problematic for this kind of stuff? Okay.
Yes, this is one more problem for all these sorts of models.
Okay, thank you very much for the.
You're welcome.
Matthew Lundy, do you want to go ahead and ask your question? And Paulo, I know you had some questions as well.
Thank you for the talk. I was just wanting to ask a question about the relationship between the frequency of the emitted radiation and the energetics of the system, whether we see any evidence of that relationship in the kind of observed FRB population as it currently exists. Do we see that kind of as a, is there, I was just wondering if there was evidence for that in the observed population.
In principle, we do not see any relation. Moreover, I could say that there is no such relation because, again, scattering energy is at least 6 orders of magnitude. And all these FRBs emit the radiation in the same frequency band within 1 decade of frequency. Definitely, there is no such a dependence. Therefore, this is a problem for any FRB model. How to produce radio emission in more or less the same frequency band with very different total energy budget. Because in all these models, radiation is a relatively narrow band.
Is that an observational selection effect, or is that actually, I've never seen a presentation of a radio spectrum. So is it just the observing band of the instrument?
Spectrum is very uncertain. Again, attempts to fit, for example, power law failed because this law index varies plus minus many to minus many. But this is compatible with the idea that frequency band is not very wide. Maybe there are FRBs outside this band. This means that the total number of FRBs is much larger than what we see. Maybe.
Yeah. Yes. Yeah. There are other questions. If not, maybe I have more questions about sort of propagation or screens in front. So if there were a wider frequency band, I guess you can see energy dependent absorption or whatever propagation effects or Faraday rotation or something like that. Are there any constraints on that kind of thing? And you could have a screen very far away from the magnetar that could potentially still do things and wouldn't be disrupted by radiation pressure or ponderomotive force.
Well, it is very far. There is no nonlinear effects. So in this propagation effects at large distance from the source are pretty well studied. Yeah. All this population, therefore I didn't touch upon this. Therefore, this is a special topic which people in the field know pretty well. Yeah. But there are many additional effects close to the source because this is strongly nonlinear propagation.
Yeah. Okay, but are there any constraints? This is a just phenomenological observation question, just screens, other things, Faraday gradients or anything like that that people talk about. I'm personally not that familiar with the phenomenology.
Faraday rotation gives parameters of the screen, not of the source.
Yeah, exactly, yeah.
Yes. Therefore, yes, there is a strange source with very large Faraday rotation, which implies that there is a dense baryonic cloud relatively close to the source and very rapidly varying. Yes, there are such things. But this is, I think, it's not related to the physics of FRB. Though of course, that's interesting.
Yeah. And then one question, about induced Compton scattering. In the old days for AGN, it was an important constraint that would kind of remove energy and damp mechanisms and also possibly defocus things.
Here, this is a constraint, but as we now see, the rate of filamentation, at least in electron-positron plasma, this is important. In electron-positron plasma, the growth rate of the filamentary instability is larger than the rate of induced scattering. And in this case, the beam splits into sub-beams propagating practically in vacuum, separated by plasma walls. Therefore, it's quite possible that induced scattering in this case does not work. In baryon plasma, this does not work because in this case, plasma is heavy and therefore modulation of plasma density are very small. And in this case, induced scattering places limits. For example, in the model of radiation from the shock in the baryonic cloud, people consider it constrained due to the induced scattering, and they show that it's marginally important in the observed band, but it is very important at lower frequency. It could explain the absence or small amount of low frequency FRBs. Maybe. But the situation is much more complicated because, again, in this case, there are other nonlinear effects which are much less known to the community, which could be stronger.
Yeah. Okay, maybe I'll ask Carl, do you have a question? Yeah, go ahead. Thank you.
Just a comment on your question about Faraday effects. I think if it's pair plasma which is involved, you can expect birefringent conversion of the linear to circular polarization, which would be nice for the discrimination of the plasma properties from the observations.
Again, if this is inside the polarization limiting radius, the radiation remains linearly polarized. Outside, presumably this is possible, but this is pretty far. And I would say it differently. In any case, this is inevitable in the polarization limiting region. If magnetic field turns in this region, the elliptical polarization appears inevitably. And this is stronger than beyond this region because in this case, phase difference is about unit. Presumably density decreases outwards. We do not expect large clouds of pairs with more or less homogeneous density. This is difference from the situation different from propagation in the interstellar medium, where we have more or less homogeneous plasma, and therefore Faraday effect works, and the effect is accumulated.
But if there's a high multiplicity of pair production in photon-photon collisions, then you obtain a large Faraday optical depth within the source.
No, again, yes, within the source, even if it's not large, the phase shift is huge. And therefore, we have two independent linearly polarized modes which propagate independently. Only far away where plasma density is small enough, one could, and therefore the phase difference becomes smaller than pi. Only then one could expect observable effects. And what we see is determined by the structure of magnetic field in this zone, not in the source.
Thank you.
Any other questions? If we're past 10, so we can open up to general discussion of whatever you think is interesting.
I mean, I actually had a question about gamma ray emission. So, you said that there's really we've only seen these in radio, but we have looked for them both in Fermi data, which is all sky, as well as with the ground-based Cherenkov telescopes. I mean, would you expect to see gamma ray emission? I mean, should we continue looking, or what's the story for that?
From cosmological distances, hardly ever, because this emission is of the order of magnetron flare. Could you see magnetron flare from distant galaxies? Presumably not. Maybe if we are lucky to see FRB from close galaxy, in this case, we could hope to see something else beyond the radio band. But from cosmological distances, hardly ever.
I mean, it was seen from the galactic magnetar, if I remember.
Yeah, sure.
And there is a paper estimating this, and you need a ratio between high energy and radio of about 10 to the 8. So this is completely hopeless.
Yes. But again, this is magnetar. We know that no chances to see magnetar flare, even giant magnetar flare from distant galaxies. From close galaxies, yes, and we see it. Therefore, if we will be lucky to see FRB from close galaxy, probability is very low. But then, yes.
Could it be like an afterglow emission or extended emission? I don't know. Maybe.
Maybe people try to estimate something, but the situation is very uncertain because it depends on the surrounding medium. And again, total energy here is significantly smaller than the total energy of a GRB. But this is company. Therefore, even if there is something like afterglow, it is very difficult to see. Again, unless we are lucky to see very close FRB.
Thank you. Paolo, I think Maxime has
Yep, Maxime was next. So Maxime, go ahead. Yeah.
I have a question about like a low energy FRBs, like how they should emit in this case. Like as you said, like a high energy you can explain, but you don't touch a low energy. What do you think about this low power FRBs?
For example, a synchrotron shock model could explain any FRBs because there is very big dependence on the emitted frequency on the total energy. The problem is for the reconnection model in the present form when the reconnection occurs at the light cylinder where the pulse enters the current sheet. If reconnection occurs closer inside the light cylinder at smaller radius, therefore magnetic field is larger, and therefore at the same energy you get higher frequency. In this case, you could get FRB in the observed band from a weaker pulse. But the question is how to get a connection in the outer magnetosphere, but inside the light cylinder. One of the possibilities I tried to describe, but it's for a while only speculations.
Okay, and maybe Amir, do you have a question? Another question?
Yes, I mean, there is only one FRB seen in association with galactic magnetars, whereas there are hundreds of flares. And my question, if this is due to the fact that it's very difficult to detect them, at least until now, or are there any estimates of what you expect with, let's say, current FRB detectors? Or is it just, because you expect many of them in post-model?
Yes, in fact, this means that a small fraction of magnetar flares produces FRBs. Why, for example, in the existing model, you see there are many additional assumptions. For example, in the synchrotron shock model, which is developed much better, we have a strong assumptions about the pair loading and so on and so on. If these assumptions are not fulfilled, then there is no FRB, or at least this FRB is in the wrong band or something like this.
But are there any actual estimates? Because, it should be before the dedicated FRB detectors were built, it was practically almost impossible to catch one because you don't have monitoring of magnetars, right? I mean, it's like a millisecond flare, and if the radio telescope says relatively, I guess, not very large field of view. So, but the question if there are any systematic estimation of what is the ratio you expect to see?
Expect from models, you see this.
No. Yeah, let's suppose that any flare emits radio FRB, for example. What's the fraction you expect to detect actually?
In all this model, a significant fraction because there is no strong beaming. Therefore, I suspect that not all flares emit FRBs. There is no reasonable mechanism for strong beaming in this case. And therefore, of course, they are not isotropic, but in all the models, they emit within a large solid angle.
But what is the coverage of current detectors? I mean, you know, they have to be within the field of view, right? So
do you mean radio telescopes?
Radio telescopes, yeah.
Yes, but you know, people especially study the giant flare 2004, because it turns out that one of the telescope could see this in one of the side lobe, and they didn't see anything. Therefore, at least in this case, practically for sure, we could say that there were no FRBs. I'm not acquainted of any statistical study of how many telescopes, what is probability to see in one of the telescope galactic flare. Maybe somebody did this, but I don't know.
That's a good question. I know that the CHIME telescope has a large field of view as in steradians because it's a synthesized array. So there's new things with very broad fields of view.
Yes, now the situation is much better, of course.
Yeah.
But you only have like a few dozen, 1 or 2 dozen magnetars, right? Scattered out. There are not so many many flares, but not so many magnetars.
Yes.
Yeah. Okay, looks like Kota has another question. So, yeah.
Can I have one more question? So the other thing that from M81, I think that there are some people just find the 100 nanoseconds variability or the time structure, right? And in my understanding, it's challenging to explain this by the scattering effect. So in your model, such a very short time scales are kind of related to some magnetic island size, or just I would like to hear about what is the origin of this kind of 100 nanosecond variability.
No, I think all this fine structure should be attributed to the propagation effect. For example, to the modulation instability or something like this.
Oh, so you think that, but this requires a very extreme parameter, right? If we want to attribute this to the scattering effect, I think that if we want to use this Sobati et al., this kind of effect, you need a very large density or something like that, right? To have a 100 nanoseconds. 10 microseconds, 100 microseconds, is relatively easy.
Presumably, yes, you're right. It's not very easy. But again, all these sorts of processes, we only started to study. Maybe we'll see something else.
Okay, so
the Crab nanoshots are explained by plasmoid size, right? So in the reconnection, in the pulse interaction with stripe ring, what we see, we see this secondary current sheet with small plasmoid forms, and we actually see some spikes. So it's,
Yes, but in this case, there are very many of such spikes because total radiation power is very high. Therefore, I'm not sure that we could see single spikes like in the crab. Crab, total radiation is very weak, and therefore we could see single spikes. In FRBs, the situation is different. The observed power corresponds to so many spikes. It's not very easy, but maybe there are some structures in the current sheet. I don't know.
Okay, so do you think that in principle, is it possible to attribute such a, but suppose that if we start to see such a short time structure, say that less than microsecond, then this kind of information can be important for the mechanism itself, right? Because if you start to see the many such as subparses, and then maybe I think that may be more difficult to explain this with scattering effect, right? Because you require the extreme parameters, then maybe we might need to think about some structures in the island, or maybe even just below the right, smaller than right spindle or something like that.
Maybe, of course. Maybe.
I see.
It is very difficult because extrapolation from this estimates, and even from simulations to real parameters, is very difficult. We have to extrapolate many orders of magnitude.
Yes, that's true.
Therefore, we must be very careful.
Can I make a comment? If I'm not mistaken, usually when you see a complex pulse, you see also the said trombone effect. They are sort of correlated, and yes, in many of them. So it's, you know, how do you explain it? By, you know, some propagation or whatever?
No. The standard explanation is that because everything propagates outwards, the frequency decreases. There were even some models and some attempts to model this within the specific synchrotron model. In this case, the problem is why we do not see this for each FRB. Again, there are many effects which are not modeled properly. For a while, all these models are very preliminary. All of them are based on very vague estimates. Therefore, hopefully they could explain the basic parameters more or less consistently. Discussing fine effects is very interesting. Maybe some of them could be explained, but even if some model does not explains properly some fine effect, maybe it's not very. It's not catastrophe for the model.
Could I ask a question maybe for the MHD model? What if the reconnection is somewhat like Lorenzo said, maybe somewhat chaotic because it's a cascade from various scales, so the guide field changes. So you don't always get a nice current sheet when you have 3D reconnection. Would that alter the conclusions for polarization and things like that, and maybe reduce coherence, or is that some limit on a cell and then which dominates? You could imagine different regions with different polarization directions lighting up. Do you see that?
I think that the real structure of the reconnecting sheet is indeed very much complicated, and therefore I'm worried that this could affect, first of all, the total power of emission. It could be much smaller. As to the polarization, we don't care what happens in the current sheet. Polarization is determined by the field outside. The field outside is more, in magnetically dominated systems, this is more or less homogeneous. It couldn't be chaotic. Therefore, polarization is not a problem. But what we need that practically, I would say, each merging produce something. But if merging occurs within a wide region of many, if the effective reconnection region is wide, merging inside does not affect what happens outside. We must perturb outside magnetic field. And therefore, the real picture may be much more complicated.
Okay, thanks. Any other question? I can keep asking if this. There was no other question. My question was, there are other places like in AGN, people talk about boundary layers where you could have shocks, relativistic shocks in pairs. Do you expect, why don't you see emission like that? Okay, not in millisecond timescales, but strong coherent emission from AGN, for example, in some parts.
I suspect that the frequency is too low. Because Larmor frequency is very low in these cases, but it should be estimated, but it's very easy.
Okay, because people have observed.
This is the relativistic Larmor frequency.
Yeah.
It could be estimated, but I suspect it's very difficult to get radiation at the observed band. We need very strong magnetic field.
Yeah. But maybe if we forget about FRB, just as a general coherent emission mechanism, say in AGN jets, you do observe very high brightness temperatures, like you see scintillation. So the source has to be very small in, let's say, gigahertz radio. So it's a more general question, that class of mechanisms you're using for FRB, could it be applicable to AGN jets in a perhaps different frequency regime, but still we expect some coherent emission because we have relativistic shocks and things?
Again, both this mechanism radiated the Larmor frequency, or not very high harmonics of Larmor frequency. Mm. Therefore, it is very difficult to get radio emission from this mechanism in systems with a relatively low magnetic field. Therefore, we need magnetar or something like this. Mm-hmm. Of course, it should be checked, but it is easy to check because frequency could be estimated relatively easily. But I think that in AGNs where magnetic field is very weak, it's very difficult to see how this mechanism could produce something observable.
Okay.
So Paulo, we should be mindful of time. Yep. It's almost out of time. I know people are leaving. Yep. So we can continue discussions, but let's just officially stop here. And I just want to thank Yuri again. Very nice talk, and please send us your slides so that we can post it. And I also want to thank the participants, for people who've been joining this series so far. As you know, today is the last day for the season. We just had a focused season on extragalactic active galaxies, theory, phenomenology, and this was a very nice talk on FRBs. We will suspend for the summer. I've posted the link to the events page on the chat. So please look at it. We have archives of all the talks, and it's a great resource for students, especially because we've also linked the readings as well as the YouTube lectures. So take a look, and we will come back in the fall with a new focused series topics. So I just want to wish everyone a happy summer and hope to see you in the fall. And Felix, maybe you want to say something, and Paulo, if you want to say something as well. So Felix, I know, has a train to catch. You should go first.
Felix, we don't hear.
Yeah, I'm just in a really rush. So sorry, I just want to, Reshmi, I want just to add some few words. And I think we could, these seminars, I could call a success story. I hope I don't exaggerate, because when it started, actually idea was with Paulo, Reshmi, and Yuri, idea was just to, some with others like Andrei Belaborodov, idea was to be connected and to discuss during the COVID some topics. But it's personal opinion. I think it was more than we were hoping for. I think you could look at the participants of the seminars. It was very, very impressive. So many experts and regularly attending the meetings. So that was, I could call it as a success story. And that was not simple, just standard Zoom seminars, but something more, in my opinion. And so we decided that we should continue, even COVID hopefully is over. And because you never could get so many experts in a room to discuss all these exciting topics. And that is really very necessary these days, to have many opinions and opinions of experts, because we are typically discussing quite hard, very difficult problems and questions. And but we want to have something a bit go beyond, to have more some regular meetings, workshops, and even summer schools. So I don't like to say more now, but we hopefully will surprise you and will come in fall. We will announce some new type of events, but these meetings will for sure continue. So thanks all to all participants, and see all of you in few months in fall. Yeah.
Thank you.
Thanks,
Thank you, Felix.
And thank you, organizers.
Thank you, everyone.
Very good series.
All right. Okay, thank you.
Okay, thank you.
Bye-bye.
Bye. Bye.
Bye.